Alright, hi. In this video, we are going to talk about the projectile of a bullet, and more specifically, we will employ the formulae we have used so far, we have derived in cases of various kinds of projectiles, and we'll employ it to a particular case of a bullet. So usually, what really happens is the fact that bullets are, well, you can imagine a case in which they are thrown at a horizontal direction. So that is to say, initially, somebody would point the gun straight at a target, say right there, and then the bullet will sort of take a very straightforward path. However, what we do know is the fact the bullet will slightly, ever so slightly bend down, and we continue bending down till the point gravity stops acting at it, which never really happens. So the body or the bullet here will assume a projectile because everything that is describing its dynamics has been describing the dynamics of projectile motion in the examples we took before. So that is to say that the motion of a bullet, even though it seems almost linear, is ultimately a projectile motion because of the fact that gravity acts in the downward direction. Alright, so we want to use the formulae that we have derived so far and see how they are applied in this particular scenario. Alright, so let's begin. Alright, so here we have a bullet which is thrown horizontally, that is at 0 angle of elevation. So that is to say that theta equals 0. So that means that because we're measuring theta from the horizontal, if the direction that the bullet assumes initially is horizontal itself, then the difference in those angles is 0 because both of them are horizontal, and theta, which we've employed in our previous definitions of projectiles, will be 0 in this case. All right, so that is a key point of observation here, or the fact that this is the information we're using to set up this situation. All right, so that's kind of important, and that is going to change many things than the normal projectile that we have so far examined, which would be something like that, or even more general case, which was something like that. All right, in which we're throwing it at from a specific height. Now, you would notice that if you hold a gun in your hand, the gun is not placed at the ground, right? So the reason it travels forward is because you are also holding it at some height. Now, we assume that that initial height at which you're holding the gun while aiming at the target is a height of h sub 0, all right? So that is an initial sort of parameter in this motion as well, right? And also, we would assume that there is an inherent velocity at which the bullet moves, or the bullet leaves the gun, and that is the velocity of the start, and that starting velocity would be, say, v sub b, right? And with the arrow pointing in the x cap direction. So that is all that we need to know in order to describe this motion. All right, so let us recall the formulae that we know for a projectile motion. All right, so that means we are looking at a very general situation of a projectile like this, with the initial height of h sub 0, all right, and the ball was thrown with a velocity v, the velocity of u, all right, that's what you've used, and the theta of elevation was, theta, the angle of elevation was theta, right? So we had a few definitions. The first one was h max, which was the maximum height that the body or the object assumes from its initial position at which it was thrown, and that is what we call as h max. And that h max height will be u square sine square theta divided by 2g, and g here is the acceleration due to gravity, which is also the same in the case of the bullet. The other thing that we worked out was the fact that there is something called as the range, and we denoted it by capital R. So that range is equal to, well, it had a rather funny formula, but the key way to remember that was, that would be the time of flight, whatever the time of flight was, multiplied by the horizontal velocity of the body. Now in that case, the horizontal velocity would be u cosine theta. And why would it be horizontal? Well, because in the entire time in which the ball has fallen down, right, which is happening in both the cases, in any projectile the ball ultimately goes down, in that amount of time, the distance that will cover horizontally will be due to its horizontal velocity, and solely due to that. And since the horizontal velocity holds constant throughout the motion, then that is basically, it reduces the entire problem to the problem of constant velocity. So therefore, the distance that you travel with a constant velocity is the speed at which you're traveling multiplied by the time of the duration for which you travel. And since the time is time of flight, and the horizontal component of velocity is u cosine of theta, in that case the range should be t u cosine of theta, right? But that again doesn't give us complete information because we really don't know what the form of time is from this expression. But we know from our previous derivations that the time of flight in this situation happened to be, well, if you recall, u sine of theta plus the positive root of u sine of theta square plus 2g h sub 0 divided by, well, divided by small g, which was again the gravity, value of gravity, or 9.81 meters per second square. All right, so this was 9.81 meters per second square to be really precise. Many people just assume it to be 10, all right, because it doesn't really matter. So these are the three attributes of this projectile motion, all right? H max, range, and the time of flight. Now, if I can evaluate what t is, I can simply put it here, and then I would get what range is, and then, well, I can also calculate H max just by knowing u and theta, all right? So let's try to employ this situation in our question at hand, all right? So in order to do that, let me change the color again. Right, so what do we know about this motion? Well, in this motion, since the bullet is being thrown at 0 degrees, theta is 0 degrees, all right? 0 degrees or 0 radian, it's the same thing. Now, if this is at 0 degrees, then we know two things. Well, sine of 0 degree is 0 degree. Oh, sorry, 0. It's a unitless value. This is a unitless value. And cosine of 0 degrees is 1. And that is again a unitless value. So we have the sine and the cosine of the angle that we will be asked to evaluate later on. All right, so we have that information at hand already. Now, the other thing that we need to know is in this case, the u velocity that we were referring here is basically VB is basically u. All right, so that is another substitution that we need to be aware of. All right, so that is something we take into account. All right, so now with that kind of knowledge at hand, what do we do is we try evaluating certain things. All right, so let's begin with the time of flight. Time of flight. Okay, so if we want to evaluate time of flight, well, we basically need to substitute u and whatever the value of theta is, and we take g to be g. All right, we don't really specify its value in this case. Let's treat it as a variable. So time of flight, again, we'll have to employ this formula, which is u, and this is in this case u would be v sub b. Now sine of 0 degrees plus root of v sub b sine of 0 degrees again, and you take the square of that plus 2g. And what about the initial height? Well, the initial height is h sub 0, so that goes as it is, and we divide the entire thing by g. So if you do that division and we evaluate all this, well, what do we know so far? Well, we know since the angle of elevation is 0 degrees, sine of theta is 0, that gets rid of this term, and that also gets rid of this term. So what we are left with is, well, 2gh naught in the roots in the numerator divided by g. Now if you do this, it turns out to be 2h naught by g root. All right, now this is a key observation. And why is that a key observation? Well, because if you think about what's happening to a ball that you basically let loose in mid-air, right? And you say, well, if the initial height of this ball was h, and I want to evaluate at what time will it fall to the ground. If its initial velocity was 0, all right, in that case, basically we are asking ourselves the question of what is the time of its flight. So do the same thing and you recognize that this is the same answer. Let's try to do that. Well, if the ball is falling down, then the displacement vector would be minus h. Well, let us assume this is y cap, so this would be y cap. All right, and the initial velocity vector is 0, so we don't really need to specify any direction vector because that will just cancel out. What about acceleration? Well, acceleration would be minus g y cap, all right, because it points in the downward direction. So use these three information and get t. So we can figure out what t would be using s equals ut plus half a t square. And if we do that, we get, well, you put the value, this becomes minus h, u is 0, plus half, and then this is minus g, t square, and you solve this and you get the same value. What does that tell you? Well, the time of flight for this bullet going down when it was thrown at an initial velocity which pointed basically in the horizontal direction is the same as if we threw a ball at this point and we let it just fall down without giving it any velocity in the vertical or in the horizontal. So what really matters in this cases of time of flight is the fact of what is their vertical velocity, because if you see this ball which was just let go and this bullet which was thrown horizontally, both of them had 0 vertical velocities, and in that case the time of flight was the same. So it really matters what the vertical velocities are if you want to vary the time of flight. All right, because if the vertical velocities are the same, it turns out that the motion are very much the same, specifically in the cases of time of flight. So that is a key observation here, which helps us to understand many other dynamic factors. All right, so that is really good. Well, now that we know that, we can get rid of this, and so that's good information at hand. What about what about the range? All right, so we can evaluate the range at this point because now we know what t is. So the range would be u cosine theta. Now remember, u was v sub b, and cosine and theta was 0 degrees, and we multiply that by t, so that would be 2h0 by g, and basically put the values of cosine of 0 degrees, which was 1, so this becomes 1, so you get v sub b times 2h0 by g, so that is the same thing. So basically the entire velocity that really helps it cover the range of the motion, which is, well, this is your range of motion, that the entire velocity that is basically v sub b, because remember all this velocity is aimed in the horizontal, so that the entire velocity is used up or sort of is contributing to the range of the motion. All right, so because there is no vertical component, we say the entire velocity is contributing to the range. If there were a vertical component here, if the ball was thrown at an angle like so, then only the horizontal component would be contributing to the range, right? Here, because there is no vertical, entire velocity is contributing to the range of the motion, all right? So that is taken care of. Now let's evaluate what h max would be. Well, put the formula back in. Again, u is v sub b, so we take the square of that from here. Then we take sine square of 0 degrees and we divide it by 2g. Remember, sine square was, well, 0, so this cancels out to be 0. That makes this numerator 0, and that makes the entire fraction 0. So that tells us that there's something strange about this answer. It tells us that the h max is 0, and that gives us the impression that the ball is really not is not really covering any vertical distance, but it somehow is here, right? Because it's covering this h sub 0 as its vertical distance. But it turns out there's a very key subtlety involved. And that key subtlety here is the fact that, remember, h max is the maximum height that the ball attains with respect to its original position. So this original position is this, and the maximum height was that. Now remember, in this case, since the ball continues to fall down, the maximum height is the initial position itself. And so if you subtract that maximum height position from the initial position, which is the same point, the vertical displacement in that case is 0. So that is why you get the value of h max to be 0. But remember, the maximum height for the entire projectile, which is not h sub max, but in that definition would be h0, because remember we added h max to the initial height, and that was the maximum height attained. All right, so pardon my handwriting right there. So that's the maximum, well, the maximum height in that sense which was attained. So in this case, that would be 0 plus h sub 0, which would be h sub 0. All right, which is true because the maximum height in this entire projectile is the height at its initial point, and the initial point is controlled by us, is controlled by the height that we initially supply it with, and that is h sub 0. So that now makes sense. All right, so these are the key subtleties that kind of show up in different problems, and I hope you were able to understand how we employed these formulae for h max, range, and time, and we were able to evaluate what's happening in this particular scenario, which we took a rather simple case where initial theta was 0. All right, so we basically used the formulae and we evaluated time of flight, and using that we evaluated range, and then we saw what really happens to the height, h max, and then we got justified why is it 0. All right, so I hope this video made sense, and stay tuned for more videos. I will be posting a few more videos about projectile motion. If you have any questions and doubts, please do mention them in the comments. I'll be more than happy to help you out with them, and stay tuned and all the best.